Okay, recording has started.
All right.
So
Fantastic.
my partner uh, for this user group, Jared Karney, is going to be speaking about introduction to column store indexes, and it's something that I know nothing about, and um, so I'm interested in hearing about this. They Jared is as I said, he's part of the Chicago Data Professionals user group. He's one of the organizers, and Jared's works for Microsoft, and he's a customer engineer. Did I get that right?
Yeah, you did. Formerly known as Premier Field Engineer or PFE. So now we're CE. Yeah. Well, cool. All right. Well, cool. Thank
Yes.
you,
I'll shut
Ross.
up now.
No, that's cool. All right. I guess we're good. Good evening, everybody. So as Ross said, and you've already heard me talking a little bit, my name is Jared Karney, and I'm a customer engineer with Microsoft. And tonight I'm going to talk about column store indexes. Now, there's going to be some things that are relatively detailed in here, but there's also a lot of detail I'm going to be leaving out because we just don't have enough time. Column store indexes can be very nuanced, and you can do some really cool things with them. But I'm going to try to make this an introduction so that everybody hopefully I can pique your interest into looking into using them in your projects in your databases that you're currently working with. And I'll give some example as to how they can help out. I can get it. All right. So we're going to start talking about B-tree indexes really quick, just briefly. Most of you probably know how B-tree indexes work, our regular row store indexes, but I'm just going to touch on them because it's important to understand how those work in order to talk about column store. Then I'll go into column store indexes, talk about how they work, some of their properties, index maintenance on them, and then we will finish up with some demos and then talking about maybe some architecture and why you'd really use column store and how you could apply it to some of your existing tables. Okay, great. So B-tree indexes, right? B-tree indexes are a row store clustered and non-clustered indexes. These are ideal for OLTP or online transactional processing. What does that mean? Right? If you're not familiar with that term or you've heard it, it really just means singleton inserts, updates, and deletes. Right? If I am a user and I've logged into, let's say, your airplane ticketing system, there's going to put in a single row for Jared. And then if I go and I buy a ticket, it might add 1 or 2 rows, or maybe multiple rows across multiple tables because it's a normalized database traditionally. But ultimately, we're working with like one set of rows that are all particular to me. And if we're talking about Ross logging into that same system, the system is going to be working with his rows, not mine at all, right? And that's online transactional um, uh, processing, right? So these kind of individual rows coming in from different users or different entities, different applications, things like that. And oftentimes, the data is not static, meaning that once it's inserted, we're going to update it either over the course of my session or over the course of a day, or maybe over the course of several days or even months, right? So that's online transactional processing. That's our typical relational database. In this case, right, data is stored in these tables as rows on pages, like a phone book. When I do talks on non-clustered indexes, I usually use the example of the white pages. So B tree stands for balanced tree. And the way that this works, I'm going to show you a nice graphic of it, but we have like a single page that's called the root. And what that does is that kind of says, hey, rows 1 through 100, please go down to page 100 below. And if you need rows 101 through 200, the next level of information is on page 101 below, right? And so it's kind of like we go through some steps, and you'll see an example of this. And seeking a B-tree index is how we reduce the amount of page reads, right? The whole point of having indexes at all in a database is to make our queries faster. That's it, because they do take some overhead to maintain as we're doing our inserts, updates, and deletes. So really, those indexes are making our selects, for the most part, faster. Okay. So this is what it looks like. So in this example, we're going to say that we have 50 rows. Okay. And each one has an ID, 1 through 50. Okay. And the root node of our index would basically say, hey, we do this table has rows 1 through 50. And if you want to find a particular row, I can tell you how to find it. So let's say I go out there and I have a query and I say, go ahead and give me row number 2, right? What this is going to do is it's going to start by going to the root node, and it's going to say, hey, I need information about row number 2. And it's going to say, oh, no problem. Go to the next level and go to the first page in the next level. Okay, great, thank you. So I go to the first page in the next level, and I say, I'm looking for row number 2. And it says, oh, great, I know where that is. Go down to the first page in the next level. And when I get down there, it says, I've got row number 2. Okay. So in doing that, in this particular case, I've done 3 reads. I read the first page, the root node. I read the next page in the intermediate level. And then I read the first page down in what's called the leaf level. And the leaf level contains all of our data in a clustered index or a clustered table, depending on how you call it, or it contains our key values and a pointer to the actual row in our main table in a non-clustered index. It also, in a non-clustered index, it will also contain any included columns. Okay. But the idea is that we step down in order to do less reads. Well, how is that less reads, Jared? Why didn't I just go to the first page down there? And the reason is because in this particular case, we were in that type of order, right? But if SQL Server doesn't know how to get to that page quick, it has to read, which is called all of the pages, which is called a scan. So if I were to scan this table to look for number 2, I would have to read, I would skip those first 2 parts, the root node and the intermediate level, but I would have to read all of the rows down below in the leaf node. Okay. And that's the difference between a seek and a scan. A seek allows me to step down and reduce the amount of reads. Whereas a scan, I skip those other 2 levels, yes, but I have to read every single page in that leaf level, 1, 2, 3, 4, 5, right? So this is how a B tree reduces the number of reads. Any questions? Okay. Great. So this is the structure for a clustered index and a non-clustered index. Okay. In our normal good old row store indexes. And then, like I said, the clustered index, all of the columns in the table are stored on those leaf nodes, right? All of the columns. In a non-clustered index, the columns that I specify as my keys, technically the clustered key, because that's how I look up back to the table if I don't have all my data here, and then the included columns. Right, so this is great because for online transactional processing, this is really helpful, right? We insert a row, we also insert a row into each non-clustered index, and we can keep it in a particular order. Non-clustered indexes and clustered indexes that are row store are in a particular order that we told it to be in, right? Which makes sense. If I go to the white pages and I say, I would like to find everybody with the last name Karney, the white pages is designed for that use case because it's ordered by last name. And so all I have to do is flip to the Ks, right? It's not really a B tree, but I go to the Ks and then I can look for everybody with the last name Karney. Or I can go to the Ks and within the last name, it is then sorted by first name. So if I'm looking for Jared Karney, I could very easily find Jared Karney. The problem comes in, and this is where a scan would be, is if I'm looking for everybody with the first name Jared. Well, unfortunately, our index, our white pages, isn't ordered by first name except for within last name. So if I have to find everybody with the first name of Jared, I have to scan the white pages or read every single page. But this does handle individual row inserts very well. It handles deletes and updates because it's easy to remove a single row relatively. Okay. So these are the benefits of row store indexes. Singleton lookups, right? We're typically looking at one or a few rows from a particular order. But these are not necessarily helpful if I say, I need to total all of the sales from my company. And then I need you to group it by year. That's fine for a small amount of rows. But when we start to get into the millions and maybe even billions of rows, that can be problematic. If we have people that are constantly reporting off of these rows, right? Meanwhile, another process is trying to insert into it or update it, we can get concurrency issues. So part of the problem here is that number one, when we're reading every column. We don't have a choice. When I go and I request a particular value or row from a row store table, because the data is stored in rows, I have all of the columns, even if I'm only requesting a few. Okay. So that's one problem, especially if I'm doing large analytical queries on only a small amount of the columns. I still have to read all the other columns, which ultimately means I have to read more pages. Compression also has to work with multiple data types. So if you're used to using compression to help with some of your size of data and performance, you can actually get performance improvement from page and row level compression. Because we're compressing a row and then a page, we have to work with multiple data types, which means that the compression algorithm that's used there can be a little bit unpredictable or not as efficient, right? Because all the columns are stored on a page. So we have to work with a row first and then a page level. And then again, you get excessive reads for scans, i.e. analytical type queries. So in a relational database, what Microsoft came out with for SQL Server was a solution for those analytical type queries. And I'm going to say for data warehouse type workloads, but the reason I'm saying data warehouse type workloads is because oftentimes we are running data warehouse type workloads against our online or OLTP databases or tables. And one of the main reasons for that is people want their data real time in certain cases. It's important for us to be able to make decisions about the business faster. And in order to do that, we need our data in real time. And so Columnstore can help us with that, and you'll see this. But Columnstore is also just super beneficial for your traditional data warehouses that are out there or tables that are functioning as such. Okay. So how does Columnstore work? Okay. And this is just very much in general because there were some changes from 2012 to 2014 to 2016. The column stores that I'm going to talk about today are primarily in 2016 and later, because that's really where the functionality shines. I just want to make that clear. Okay. So how does this work? Rows are divided into groups called row groups. And oftentimes we see this represented and talked about as optimally being 1 million rows. It's not exactly 1 million. And so I don't like when people just say 1 million. To me, that's not helpful. It's 1,048,576 rows is an optimal row group. That is the maximal amount of rows that can be in a row group. Okay. Now the data within this, when it's put into the column store, is stored as individual columns. So instead of a page containing all of the columns, a single page only contains data from a single column. And because this is highly compressed, and these are also read-only column segments, they are stored as lob pages. Lob pages are large object pages. So they're not what we consider typical data pages like we do in RowStore. It's binary and it's highly compressed. And the reason that we do that is because, as you'll see, we can get some of this great compression by removing duplicate data and just having pointers. So it's a proprietary binary format that makes it much more efficient at storing this type of data. So what is the column segment then? The column segment is a particular set of rows from a row group, but for a single column. So let's kind of take a look at how this works. Right? Each page is going to have data from a single column. So in this case, if I insert, let's say 1,000 rows, or let's say 1,000,000, right? We're gonna stick with that. I'm gonna throw on my pointer here. So I insert a million rows, 1,048,576. Okay, and so that is all one row group. What the Columnstore does is it will take that 1,448,576 rows. I'm going to start just saying 1,000,000 because it's much easier. And it will break those rows into its individual columns and compress all of the data for that column onto a single page. The order of the data, or the linkage between the different columns for a particular row, is maintained. Okay, so we still know we're not decoupling the data in column 2 from the data in column 1. That relationship for each row is not lost, but we're storing them in a separate location, if that makes sense. However, the optimal use for a column store is that I may not necessarily care about that linkage too much, because I may be aggregating everything in column 2 and I don't care about the pieces that are in column 1 and how they relate to column 2, right? Let's say column 2 is sales, right? And I'm just getting a total sales. Now, when we start to say, okay, well, column 1 is the sales date, and I need to group this by sales date, then we do start to care about that relationship. But it's a less strict relationship, because if we're using a clustered column store index, meaning that is all of our data, all of the columns, we should not be doing too many singleton lookups, updates, or deletes. If we are, then maybe a clustered column store index isn't what we need. And we might be looking at a non-clustered column store index. Okay, but this is how it breaks it up. So it breaks it up into these row groups. And what's really awesome is because each column is the same data type, we can get a really significant compression ratio. The other great thing about this is when you are selecting or working with columns, a subset of the columns within a table, we don't need the columns that you aren't requesting. So if I am saying, go ahead and group everything by column 1 and sum it by column 2, all of this stuff over here isn't even read off of disk or into memory. So we're reducing the amount of reads, right? If all of our data from those 1,000,000 rows, and this is just a kind of a, it's not going to be an exact example, but let's go with this analogy. If I insert this into a row store and it takes up 1, 2, 3, 4, 5, 6 pages of data, and I say, well, Jared, I just need column 1 and 2. In a row store, I have to read all 6 pages of data. to get all of that data. But let's say I need to read all of the data, like all of the rows, but only column 1 and 2. Now I'm only reading 2 pages, right? And when we start to talk about the benefits of Columnstore, we're talking about millions, right? Because we're talking about a row group having about a little more than 1 million rows. So presumably, we are having millions and millions upon millions of rows in this table, which is much more common these days than it used to be. Okay, and so those reads become very significant, reducing those reads. And then also the segment elimination of saying, oh, he only needs column 1 and 2. Therefore, I don't even need the rest of these. Right? That's awesome. So each column can be accessed independently. Each row group also stores some really awesome metadata about its column. So it'll have like the max and the min. So that if you're filtering, it might come over here and say, oh, you're looking for dates that are greater than May 1st of 2021. Well, the max date in this particular row group for this column, because this one holds the dates, is actually January 1st of 2021. So we don't even have to look at anything in this row group. So we just cross out this whole row group. All we did was read the metadata here. We don't have to read anything in this row group. Go look at the metadata of this one. Oh, this one doesn't fit either. Skip that. Now we come down here. We say, oh, the metadata meets it. We need column 1 and column 2. So we just did 2 reads, right? Instead of maybe all of these reads that it would have cost us before. Is that making sense from a logical kind of theoretical point of view? Because we're still kind of theoretical at this point, right? Understanding the mechanics. Any questions?
Yeah, I have one.
Okay.
How does this work with insertion or even updating?
We'll talk about that in a minute. I'll get to it. Good, very good question though. Any other questions? And then if I don't answer the questions that you have there, you can come back. So this is what we call a column segment, right? Each one of these is a column segment. And then a row group are all the column segments that are related based on the rows. All right. Great. So part of the architecture of a column store is this thing called a delta store. And to kind of go to Ross's question, the delta store is how we handle singleton inserts, updates, and not deletes, but inserts and updates, right? Because I told you that the column store, once it's compressed, is a read-only structure. Okay, so how do we still allow this to be OLTP? Well, the delta store is a B-tree structure. Right? So you can almost think of it like, let's say we have a clustered index over here on table A, and then table B is a column store, a clustered column store. And then we go out and we create a view against the two of them doing a union. That's kind of what's going on here. Okay, so it's a staging area for our incoming data, and it is just like our typical row store setup. It's a B-tree structure. Okay, so inserts go into the B tree, and it's a staging area. Once that B tree hits 1,048,576 rows, it will be, quote, closed. Okay, so when inserts come in, or updates for that matter, because updates are ultimately an insert and a delete, but I'll get more into detail of that in a second. That B tree becomes what's called closed, and then a different process will go and merge it into the column store. It'll compress it, okay? So data comes into this B tree structure. We hit that 1 million rows. Then it's marked as closed, so it's basically locked. And then a process will go compress all of that data into the column store. And it now becomes a column store row group with its column segments. So how do updates happen, right? Well, if we're updating data, what we do is it functions ultimately as a delete and an insert. That's all you have to know. It's a delete and an insert. So how does a delete happen? A delete happens on a delete bitmap. So all we do, instead of actually touching the column store, what we do is we mark in another structure called the delete bitmap that particular row has been deleted. So anytime we read the column store, we are also going to read the delete bitmap. So basically grab the data from the column store and then subtract out the data that is marked as deleted in the delete bitmap. So an update simply adds an entry to the delete bitmap and then inserts into the B tree. How do we get rid of some of this stuff? Well, to clean all this kind of stuff up is when we get into index maintenance. So we'll talk about that in a little bit. But let me see. So Ross, did I answer your question? And are there any questions about the Delta store?
No, you cover my question. Thanks, Jared.
Yeah, no problem. Great. Okay, so what do we have, right? We've got a Delta store, we've got a delete bitmap, and we've got our actual column store. Those are the three main structures here for storing the data. Now there's another structure, right? And I shouldn't say that it's not a main structure, but it's not as much about storing the data as it is more metadata about the data. And these are called dictionaries. So I guess I would call them another main structure. Let's call them the fourth main structure of the column store index. And what these dictionaries are basically out there for all intents and purposes, to enhance compression. Okay, we've got global dictionaries, which are global for the entire column, regardless of the row group. And then we've got local, which are specific to a particular row group. And all this does is it maps frequently occurring values to an ID so that we don't store those values over and over again. It stores a much smaller 32-bit ID that maps to the actual value. So we store the actual value once, and then every row basically has a pointer to that value. This can significantly help us with our compression. This is why we can get such good compression. Okay. What is stored in dictionaries? Where do we get some of this significant compression using dictionaries? Integers, floats, and strings will be encoded in a dictionary. But there are limits to the size of the dictionary, because at some point, right, if there's too many distinct values, then it doesn't become as helpful. Okay, but we're not going to go into all the details of that. We've got our four main structures for our column store now. We've got our Delta store, which handles all our singleton inserts and updates. We've got our delete bitmap, which is functioning for our deletes and our updates. We've got our column store, and then our dictionaries, which are modified and or created when the Delta store is pushed into the column store. Okay. Any questions? All right, so that's like the structure, right? And we've got clustered column store, as I mentioned, and we've got non-clustered column store indexes. So why should I use these? I've kind of touched on that, but certainly in a true data warehouse, okay, or data warehouse table, the clustered column store is great for storing fact tables, especially when they're large, right? If you're less than 1 million rows, you're probably not really going to benefit from a clustered column store. So think about that. Okay, this is really for large tables and data warehousing workloads. It can also be used for large dimension tables. I shouldn't say just fact tables. But dimension tables many times have kind of singleton lookups, but they are static, so they may benefit from this. So your mileage may vary there, right? But the clustered column store can improve your query performance and data compression by up to 10 times. That's huge. That's huge. Right, so we use this on large tables with lots of scans and little data change.
I have a question.
Okay, go ahead.
When you say little data change, you don't mean inserts, you mean updates, correct? I mean, if you have a table that you have has a ton of inserts
Yeah,
throughout the day,
right.
but very
Yes.
little updates,
I mean, updates and deletes,
updates.
not necessarily inserts, right? Sure. No, that's a good point. Although I would say if we are only inserting, 100 rows a day, this may not be a great candidate. Of course, if you're only inserting 100 rows a day, you probably don't have a million rows, right? So the idea of the clustered column store is that the data is relatively static. And as we'll see in a minute too, and is some of the links that I'll include here, the best way to get data into a clustered column store is by bulk inserts. Okay, and there's some reasons for that, and we'll talk about it in a minute. But then we also have a non-clustered column store index. And what's great about that is we call this real-time operational analytics. All right. So there's an article that I linked to at the end of this, but this is probably like one of my favorite things and probably the most underutilized feature of SQL Server is the non-clustered column store index. So let's say I've got a table that gets lots of updates, heavy updates. I worked at a company for a while where they did this. They basically had a bulletin board of kind of all the orders or all the things that were coming in. And every time something changed with that, a status or other information, that board got updated and people were querying this data. It was kind of like wanting to have a live dashboard on your screen, right? And there were hundreds of employees constantly looking at this, which meant there were constant hundreds of queries against that entire table. And at the same time, we had hundreds of queries coming from the application updating that table, right? So if you're familiar with locking, if we've got one query going and querying all the data, it's probably trying to take a table lock. And if we've got other things trying to insert and update single rows, it's either taking page or row locks. And those things are not very well compatible. So we got a lot of blocking, right? And that's not good. We don't like blocking. We know that it needs to happen to keep our data consistent, right? And concurrent. But when we have that, it causes performance issues. So one of the ways you get around that is, and people's first thought is a clustered column store. But the in the actuality, what you want to do is make this a clustered index, a good old trusty row store clustered index, and then put a non-clustered index on Columnstore, non-clustered Columnstore index on all of the columns that are used for that bulletin board query. And oftentimes people will actually build a non-clustered column store on all the columns of the table. Okay, because we don't have multiple non-clustered column store. And that's because our column store indexes are not ordered by a particular key, right? You saw that. I didn't talk anything about order. Now there's ways and there's kind of advanced techniques to force order to really take advantage of the row group elimination for querying. And there's also some partitioning strategies. You can partition clustered column stores as well. But in general, for the purposes of this discussion, right, there's really no order because that's not the point of it. The point is to make our scans that have to read all the data and do aggregates and analytical style queries much faster. So what we would do is if this table is an OLTP table, but we know that our users need these real-time updates put together to them in a dashboard, then I'd build my non-clustered column store on that table. Right? So that all the inserts, updates, and deletes are hitting the clustered index. All of my reporting queries and my reads are hitting the non-clustered column store. It's awesome. This is what we call real-time operational analytics. Because anything that's hitting the column store, number one, is probably going to be significantly faster for its analytics than hitting the row store table. But they're also two separate structures, right? So we're going to have much better concurrency in terms of locking and blocking. Surprise, surprise, you could also do these things in memory and make it even that much faster. There's certain restrictions about in-memory OLTP with Columnstore, but it can be done. There's a gentleman I link to him, to his blog at the end of this slide presentation. So when we send that out, the link will be in there. His name is Nico Neugebauer. He works for Microsoft as well. I don't know when he started. I don't know if he's been at Microsoft. I didn't look it up. I don't think he's been at Microsoft as long as I have, actually, but I could be totally wrong on that. But he did a fantastic blog series. We're talking like over 100 posts on column store indexes, because he just dug into it and did a lot of experimentation and working and how to optimize this and that for particular workloads or for particular things. So if you do get into this, he's a great resource to look at his blog. Right, but this is awesome. But don't make the mistake of saying everything should be a clustered column store when you're in these scenarios. It might be better. And I went to a customer, and one of their biggest problems was the fact that they were doing a clustered column store index with non-clustered row store indexes on it, and they should have done it the other way around. It should have been a clustered table, row store table, with a non-clustered column store. Right? So it all comes down kind of to the purpose of the table, right? Are you doing a lot of singleton inserts and updates and deletes? If so, then it should probably be a regular good old clustered index with a non-clustered column store on it for the analytical queries. Right? In a more analytical table where you're bulk inserting rows several times a day or even once a day, then it's probably going to be served best by the clustered column store. And then you can, if you have point lookups, you could add non-clustered indexes for those point lookups for those other columns. Okay. Lots of scans is where clustered column store shines. Table scans. You can't get away from table scans because you're always reading the entire table or the majority of the table. Okay. Any questions? All right, so let's talk about data loading, because this is where the column store, like kind of understanding a little bit more of the detail is helpful. All right, so we talked about inserting data in general, but there's more to it. So number one, let's talk about, you've got an existing table out there. It's a clustered regular row store, or it's a heap. What happens when you just create a clustered index on it? So the first thing it does is it divides all your rows into groups of approximately 1 million, right? Which we saw was 1,048,576. Then those rows will be encoded and compressed into the column store. So that's basically during the index build. The same thing happens like with an index rebuild. We are literally creating a copy of the data into row groups of 1,000,000 rows, or that 1.048, whatever, and then encoding it and recompressing it into the column store. Okay, so that's creating a column store index or rebuilding a column store index. Okay. What about inserting into an existing column store? So we talked about the Delta store, right? Individual small inserts will go into the Delta store, which is a B tree table, right? And then it's closed and it'll be later compressed. That thing that moves, it always makes me think of the people mover from Epcot. But the tuple mover is what is kind of like a background process, much like the ghost cleanup or some of those other background processes. And what it does is it will take closed Delta store row groups and then do the compression. And of course, keep it available while it's doing the compression. So you have 2 copies of the data. And then once it's compressed and officially moved to the column store, it will, quote, tombstone, much like our ghost cleanup process. It'll mark those B trees as tombstoned, meaning that eventually they'll get cleaned up through a background process. Okay. Now here's where the column store gets really cool. Bulk inserts. So whether you're using like BCP, bulk insert, or even from a staging table, like select, insert into, select star from staging table. Those inserts that are greater than or equal to 102,400 rows and less than our max will all go as a single batch into a compressed column store. They bypass the B tree. Okay. So they will be placed directly into compressed row groups. If you specify a tab lock with that insert, it will do it parallel. So for instance, if I were to take, and you're going to see this earlier or later in my demo, if I were to take 300,000 rows and insert them in a single batch with a tab lock or a table lock, hint, it's actually going to insert into 4 separate column stores directly. Okay. Or I'm sorry, it'll actually split it up because it's 300,000 into 75,000 rows, which is not our 102,400, right? So it'll actually go directly into B trees, but it'll split up the total batch. So effectively, if I knew that I had 4 processors and I use the tab lock, so I can go 4 parallel, I could insert 4 million rows into 4 compressed column stores in a single batch, if that makes sense. So there's nuance to the design on how you do your inserts, especially if this is a data warehouse style and you're doing the bulk insert in a load. Okay. And if I'm inserting 1,048,577 rows, then I'll get one lonely row that goes into a B tree delta. But the rest of them will go into a column store. So it'll do that math for me. It won't just say, oh, you're over the limit. Sorry, we can't do this. No, it'll still do what it needs to do. All right, so are there any questions? Now, right, we're starting to add some kind of nuance to this. But you can now see some of the effectiveness as well of doing bulk insert. And so certainly you get even more benefits of the clustered column store when this is a data warehouse kind of load table, right? Now, one thing I'll say is that it's not really good to have closed compressed row groups of 102,400 rows. That's like a waste, right? Because those pages could hold a lot more data, right? So usually like a general rule of thumb is your batches should be, or your row groups should be at least 500,000 rows. If not, we can maintain this with our index maintenance. We're going to talk about that in a minute, okay? But we don't really like those small row groups. It's a waste. Because now we're doing excessive reads, right? If we could have fit a lot more data into that row group, then that means we're having more unnecessary row groups than we need, which means we're doing more reads than we need, right? So let's talk about index maintenance with these, right? We know about fragmentation on a B tree. Column store indexes don't get fragmented like B tree. And you'll notice that in the first bullet point here, fragmented is not in quotes. So I'm talking about the literal term like fragmentation, things getting out of order, right? A column store index is not, its purpose is not to maintain a particular order. That's not what it does. And therefore, it doesn't get fragmented in the same way. However, because fragmentation has become a term that we associate with indexes and maintaining them, Microsoft calls fragmentation of a column store index when we either have multiple delta row groups, which might be not bad fragmentation. Oh, can you all still hear me? I just heard like a buzz in my headphones. Yes? Ross, can you let me know?
Yeah, you're good.
Okay. All right, good, great. So multiple delta groups, and just like SQL Server, sometimes it's okay to have a little bit of fragmentation, right? Or even fragmentation, which is measured as page free space, right? That's okay in certain cases. We want that. So there are good cases to have multiple delta row groups, but if we get too many, it can impair the performance. Deleted rows, that is another way to measure fragmentation. If we have a small amount of deleted rows, not a big deal. But if all of a sudden we're reading all these column segments and then we're basically taking out all the data because it was all deleted, that's not fun, right? That's a lot of extra work. We're reading data that we shouldn't even have to read, right? So that's another way to look at fragmentation. And then the last one is small compressed row groups. And like I said, the general rule of thumb is to be less than 500,000. Or less than 500,000 is considered a small row group. That varies. I'm just using that number because we pull it from, we talk about it in like Synapse and stuff. But you think about it, right? If it's 1 million rows, 500,000 is a good amount, right? So how do we maintain our index? Well, there's the hammer. The hammer is a rebuild. It's an offline operation. It takes an exclusive lock on the table, okay? And it literally, just like in B-tree, it creates a copy of the index. It will read all the data, uncompress it, and then recompress it. So what does it do? Yeah, it'll get rid of all your small compressed row groups, okay? It'll presumably recompress them optimally. It'll get rid of your deleted rows. It'll get rid of all your multiple delta groups. Okay. But it's offline and it's pretty expensive. There should really be very little reason to do a rebuild on a clustered column store index. Okay. Reorganize basically does everything you need it to do. It will remove deleted rows. So when I reorganize, it'll remove the deleted rows, the bitmap, right? It'll uncompress the row groups that have deleted rows and then try to merge them all together, including the small row groups, into one larger row group or several larger row groups. Right? And there's a whole article on merge policy too. The other thing that reorganize does is it gives you the option to force all of your open delta groups into row groups. But when you do that, it will leave them small, right? So if you have a delta, and you're going to see this in my demo, if you have 4 75,000 delta groups and I do the compression or and I give it the keyword to get rid of those, it's not going to merge them. The next step will merge them. I'd have to run a reorg again without my special keywords, and you'll see that. All right, so let's get into the demo because we don't have a ton of time left, but this is where hopefully things will be pretty cool. Okay. So can you still see my screen here?
Sure can. We see a thing that says demo.
Great. All right, so I adapted this script from a link from Sunil, and this was him basically demonstrating the reorganize. But the nice thing about this is it also shows you a lot about clustered column store. So the first thing I'm going to do is I'm just going to use Wide World Importers Data Warehouse, and I'm going to look at my count of my order history table. So my fact table here of order history has 3,702,592 rows. Now this is a B tree right now. Okay, so it's just sitting there. We're going to shrink that a little bit in our new tables, just to make it a little bit easier to work with. All right, so the first thing I do is I create a test table and build Columnstore, right? So really, I'm creating a copy and just an empty table of my fact order history, and then creating a Columnstore index on it. Now, there is an identity column in here, so I've already fixed that. So that's something that would have to be done if you're going to try to do this demo. But ultimately, here's what we do, right? I'm just creating a clustered Columnstore index on a table. And notice that I give the Columnstore index a name, and I give and I reference the table. I do not give it any key columns because, again, we don't order this. That's not the point of this index, right? So really quick, what I'm going to do is I'm going to make sure that my table is truncated. Okay, I'm going to insert into my new Columnstore table 300,000 rows from my order history. So instead of the 3 million, we're just going to work with 300,000 for now. All right. You'll also notice I've got a max stop of 8, and I wanted to simulate Sunil's situation. So I'm just setting this to a max stop of 4. But what you'll see is my 300,000 rows will get parallelized out to 4 threads, which means I'm going to get 4 delta stores of 75,000. Okay, so we're going to do that first. And remember, it's this table lock hint that is allowing this to go parallel. You can do it without a table lock. Like you can insert into a Columnstore without a table lock. It just won't be parallel. And that may be what you want. If you're only doing 1 million rows, I don't want to split that 4 or 8 or 12 or 24 times, right? That defeats the purpose. I want to insert 1 million rows all at once. Now, just for the sake of looking at the table size, I also am going to insert just the row store data, the same data that's in my clustered column store into a row store. So we know we're looking at the same data. We just want to see the size, right? So first of all, you can see how fast that was. That was pretty good. If I look at my B tree with the 300,000 rows, I can see that my B tree is approximately 61 meg, and I can see that my Columnstore is approximately 68 meg. So my Columnstore is bigger. Why is that? My Columnstore is bigger, so I can use this DMV, DB Columnstore row group physical stats. My Columnstore is bigger because right now, these each have only 75,000 rows, which means what? They are delta stores. They are B trees, which means I am holding 4 B trees, which means I have 4 intermediate level pages and I have 4 root level pages, right? So even though the data itself is the same, instead of having 1 root node one intermediate level, presumably, and then the leaf level, I have 4 root nodes, 4 intermediate levels, and then my data. So there's extra intermediate and root, which is adding to the data size. So right now, that's why this is bigger than my single B-tree row store table. Does that make sense to everybody? Any questions? No. Okay, good. All right, so I'm just going to verify those are all still there. They're open. Now what I'm going to do is I'm going to use the reorganize statement. What you'll see here is at the end of this, I have added this option, compress all row groups on. So when I do that, it's going to compress my delta stores into individual row groups, right? If I run just this, nothing happened. I still have 4 open row groups of 75,000 rows. Right now, if I compress all row groups, right? Because that's all I have. All I have is delta stores right now. I don't have any actual compressed row groups in this table because it's new, right? And it's fresh data. Compress all row groups on, so it'll do that. And now if I go back here and look at this again, what you'll see are these 4 tombstone, right? So those are the delta stores that have been tombstoned. And here, oops, wrong key. Here are my compressed row groups. Still the same size. They're all still 75,000. All that keyword did was it said, Jared is telling me to take my delta stores and compress them. So that's what it did. It didn't merge them. Okay. So now if I go and I look at the space used, well, gosh, that's not cool. I see 600,000 rows. My old row store or my control still has its 300,000. It's still, because it hasn't changed, about 62 meg. But look at this. This is even bigger now. And that's okay. That's because those delta stores have been tombstoned and they have not yet been cleaned up. If I were to sit here for some time, those will get cleaned up. But let's not do that. Let's do this. I'm just going to delete 30,000 rows. And now what you see is I still have my tombstone, so it hasn't cleaned up yet. But now what you'll see here is deleted 30,000 rows. But the total rows in the column store are still 75,000. And that's important, right? So finally, I just want to make sure. All I can do here, I can do a reorganize. And when I do this, it's going to clean everything up. Now, when I look at this, my 4 compressed row groups have been tombstoned, including the deleted rows one. They've all been merged into a single compressed row group of 270,000 rows. So this is index maintenance for a column store index. I'm looking at deleted rows. I'm looking at the number of B trees or delta store row groups. And I'm looking at the size, right? And that's how I'm going to handle my fragmentation with a reorg. It's not going to touch row groups that are already full. You know, and there's an algorithm, but basically, you know, if I were to insert, another million rows, it's not going to open up this already compressed one. Now, another cool thing about this, I'm going to go back to the top and I'm going to truncate my table again. I'm going to insert back into it. So I'm going to go through all these steps again really quick. Insert those 300,000. Now what I'm going to do is I am going to compress all my row groups because that is not automatic. But while they are compressed, I'm going to delete the top 30,000. Now this is something that's very interesting. Okay. Right now, we still see 4 compressed row groups. They're still very small. But let's see if we can give this a little bit of time. Mhm. Come on. What we should see is something called, in this trim reason, we're going to see a single row get entered here, and it should say auto merge. And the auto merge is a process that SQL Server says, whoa, 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 you've got 4 mini row groups. I could do something with that. And so it will automatically merge those together for me, which is really awesome. Let's see. It didn't get there yet. We'll come back in a minute. All right, so what are the architectures for using the clustered column store or the non-clustered, just column store in general? And as I kind of touched on, right, you can have a clustered column store with or without non-clustered indexes. And again, this is for large amounts of relatively static data, lots of table scans and aggregates, analytical queries. So if we are analytical heavy versus our update or singleton lookup heavy, then we'd want the clustered column store index. If we are OLTP heavy with a couple of important but not many analytical queries, then what we'll do is we'll cluster row store our table and then add a non-clustered column store index on all of those columns. It's really important when we do that we don't have any non-clustered indexes, regular row store non-clustered indexes that would interfere. So those old non-clustered indexes that we were using to satisfy our queries, we need to drop them and let it use the column store, the non-clustered column store. And then, like I said, it can also be in memory. But when we get into that, it's really subject to some restrictions. Let me see really quick if it cleaned up for us. No, it didn't. That's too bad. It will. Let's see if I can trigger something here. What they say don't type in demos. See what happens? That's what happens. Now, selecting star, of course, isn't a very common query, right? For a column store. But let's see if that triggered anything. No, it didn't. But there are times when it'll get this auto merge and it'll take care of that for me. But in this case, remember, like I said, I can just go here and reorganize. And once I do so, I now have a beautiful single compressed row group. Right? What are the sizes? So that's the final shebang. My original B tree table, 62 meg. Now that I have a compressed column store, 10 meg, 11 meg. Right? That's pretty good, especially with this small amount of data. Imagine the savings when you're talking about millions and millions upon millions of rows. That's huge. And depending on the data types and the number of columns, that compression can be way better than this, right? So great. That is it for my talk on Columnstore indexes. Are there any questions?
What cleans up the tombstones?
It may be part of the tuple mover process as well. I don't remember exactly, but they will get cleaned up because they're B-tree. It may even be ghost cleanup. I don't remember.
Right. And I guess there's no way to hasten that process. Like do a I don't know, checkpoint or some darn thing.
I don't know, but what you'll notice when I did this, right, is that the reorg itself got rid of some of those first tombstoned.
Mm-hmm.
Now they're all gone. So, yeah, I don't know. I'd have to look that up. I haven't run into that issue. It's a good question, though. My guess is you can't. I mean, much like ghost cleanup, you know, there's really no way to hasten it. Even a checkpoint doesn't make ghost cleanup go faster. Any other questions?
Makes sense.
Do you have time or I don't know, desire to discuss partitioning in Columnstore and how they impact each other, or if they do?
I do. I'm not sure. So
Are there
give me
any,
an example.
just are there any considerations when partitioning tables that have column stores?
No,
Or
I mean, I guess there's always a consideration when you're partitioning, right? But what the partitioning will do is ultimately, right, it's putting it to a different allocation, right, or partition. So it's just separating the data, but the column stores themselves are still the same. Now, if I'm partitioning on something like, I would want to partition on something, presumably, that keeps my rows still being inserted where I need them. And when I say that, I mean, if I'm doing a bulk insert, let's say of 1 million rows, I don't want 2 of those rows to go to one partition and then the other 999,998 to go to one, right? But usually when people are partitioning on date, it's just going to help them with their backups, right? Does that make sense?
yes, I follow what you're saying. Thank you.
Yeah. You know, and again, I am a big proponent of saying that partitioning is should solve a backup or maintenance or administrative problem. Partitioning is not done to solve a performance problem, because proper indexing can always solve the performance problem. You can get a performance boost, of course, through partition elimination with the right queries, but I would not solely do partitioning just to try to get a particular query to do partition elimination. I do partitioning to solve a problem where I have a problem backing up a really large database, right? Or doing index maintenance on a really large database. So I would keep that in mind. Any other questions? There's so much more about Columnstore that, you know, I didn't touch on, and it just can't be covered in an hour or even a couple hours. Even in the workshops that we do at Microsoft, we don't spend a ton of time on it because it's just a very deep issue. It's something that is really good to either one, dig into yourself on the blogs and the documents, or two, to, that would be something you would sit down with somebody and plan a day to really discuss, if you really wanted to learn kind of some of the nuances on it. But it's cool. And like I said, I think that almost every organization has a use case for it. And whether that's the clustered column store or the other way around, the non-clustered column store. I don't see enough people using it, and I think it could solve a lot of their problems. Great. Well, thank you, everybody. Here's some important links that I'll include in the slides when I send them out to Ross. Column store index defragmentation, so that talks about the reorg. Talking about how to load into them, so it talks a little bit more about that million directly into the column store and stuff like that. Real-time operational analytics, where I really think that's probably the biggest thing I think is underused with people, is they just keep running these analytical queries against these OLTP tables, and either they do snapshot isolation, or they do no locks, and just stuff that can wreak havoc on your server. This was designed to fix that problem. I would highly suggest looking into it if that is your problem. And then finally, a link to Nico Neubauer's blog on Columnstore. Tons of great information there. So again, thank you.
Thank you. You can hear me.